Hello everyone, this is Jan from Polytechnic Montreal, and today I'm going to show you how it is possible for an artificial intelligence to drive autonomously in a video game exactly as if it were a human player. For this I will be using the TrackMania framework. So TrackMania is a framework that is developed here at Polytechnic Montreal, and it is for deep reinforcement learning targeting industrial applications. The fun story about this framework is that it was originally developed around the TrackMania video game as a hobby project, and that's why it has this example pipeline which is readily implemented and which you can use very easily even if you don't have any knowledge about machine learning or about Python coding. You can just follow the tutorials and do whatever we'll be doing in this video at home yourself if you like. But what does it mean for a human to drive in a game like TrackMania? Well, first thing, we control the game via a gamepad. Of course, for this video I will not be making a robot arm that holds a gamepad, that would be kind of crazy. So instead I will be using a library that emulates a virtual gamepad directly on my PC. Then I can control this gamepad from my Python script. Observing the screen is easy, we can just take screenshots, because if you think about it, this is what our eyes are doing in the real world with the photons they capture, right? They just transform this into an array of values, you can say, which is a screenshot. But now the real question is, what can we do with these screenshots? And this is a hard question. Part of my answer to this question is deep learning. So deep learning is a mathematical theory of the brain, according to which your brain is made of so many interconnected neurons that it is able to project very complicated structures, like images, into combinations of electrical signals that represent concepts. For instance, you can imagine that the combination 110 microvolt would represent the concept of a left turn, and your brain would be able to project the image of a left turn into this combination 110 microvolt. Finally, the brain can project this conceptual combination into another useful combination, which can literally be muscle commands. Now, what is really cool with deep learning is that not only it is a theory of the brain, but it also works in the real world. With a computer, it is kind of easy to reproduce what I've been describing, and this is basically how modern AI works. Okay, but now that we know how to process a screenshot, let us take a little driving theory test here. So that's a screenshot from TrackMania, and now the question is, what do you think you should do in this situation? Now I don't know about you guys, but this is a right turn, so I would naturally choose right. Now what happens if we do turn right? I'm sure some of you guys saw that coming, but the point is that one screenshot was not enough, right? You are basically not fed enough information from the past to understand the future effect of this action that you are trying to choose. So how do you choose an action if you cannot predict its future effect? Well, you can't. So instead of a single screenshot, what I will be feeding to my AI is an history of 4 screenshots equally spaced in time. This is like a mini video where the AI can see linear and angular dynamics such as velocity, acceleration, etc. Okay, now do we have enough information to predict the effect of our action? Actually, not quite yet. Something that you might not know about your brain, although it is very interesting, is that when you are looking at the world, what you are seeing is in fact the future. I know that sounds a bit strange, but here is the plot. Imagine that you are catching a ball, for example. The ball moves very fast, and yet it takes several dozen milliseconds for the information captured by your eyes to even reach your brain. But that's not all, because once this information has reached your brain, it takes your brain 120 more milliseconds approximately to be able to even react on the basis of this information. And yet, you don't really notice this delay. Why? Because what you are seeing in your head is in fact a prediction. It is a prediction of the moment when the action that your brain is computing will finally be applied in the real world. And this prediction is based on 2 things. It is based on what the brain receives from the eyes, which is past information, and also based on the action that it knows it is currently performing. So in TrackMania, on top of my history of 4 screenshots, I will be using a history of 2 actions here. One to account for the time required to capture a screenshot, and one to account for the time required to compute an action. Finally, because these quantities are easily available to real-world self-driving cars, I also give my neural network the current speedometer reading, the current tachometer reading, and the current gear. This is made possible by the OpenPlanet API, which I also use to compute a very nice reward function. Now, why do I need a reward function? Well, I did tell you it is possible that the brain processes images, but what I haven't told you about is how to find these very complex projections that transfer, let's say, images to conceptual combinations. Here, for instance, I am using a CNN to process images, but you can see that this CNN has no clue what to do because it is in fact initialized entirely randomly. So, to train my CNN to complete the task, I represent the task in terms of what we call a reward function, which is a function that has high values when the network is doing good at the task and low values when it is doing bad. And now, all I have left to do is tune my neural network such that it maximizes this reward function. This is, let's say, the entire idea of deep reinforcement learning in general. And for the actual algorithm that I will be using, this is an algorithm called soft actor critique. If you want to do some research on why, I encourage you to do this, it's very interesting. I just won't explain too much because it's a bit out of the scope of this video, I guess. So let's just see what it's doing in practice. Okay, to train my CNN first, I will be using this visually simple track. Technically speaking, it is quite difficult, it has many sharp turns, but in terms of visual features, it is very simple. You have only plain flat road with black borders on the sides. So it should be doable for a CNN to learn to see these simple features. Also, some of you might remember this track because Gwen and Afi, who are the champions from the TM Cup, ran against one of our previous AIs on this very track. This previous AI was very limited in terms of what it could do, so it could only have a hope to run on plain road with black borders like this. Why? Because it was not looking at actual images from the screen, it was instead looking at a vector of 19 rangefinder values that we would compute with a simple trick, which was to compute the distance from the middle of the screen to these black pixels on the borders of the road. Of course that was very limited, but that worked. So that gives us a baseline, and the baseline performance of this previous AI was about 46 seconds. So if we can reach something like 46 seconds with this new AI which actually looks at the screen, I will personally be very happy. Wow, this was 6 seconds faster than the baseline. Now, what is really interesting is that the previous AI, the baseline, was very conservative, was not touching walls at all. Whereas this new AI is ramming into walls like there is no tomorrow, and yet it has a much better performance. Why? Because look closely enough, it is not just ramming into walls crazily, it is using the walls in a somewhat clever fashion. Either it is bouncing on the walls to find itself in a better orientation for the next part of the track, or it is actually using the wall as a means of losing speed. Of course, if you play the game, you know that this is not the optimal thing to do, but it seems to be the strategy that Soft Actor Critic found. And for DeepRL, it will be probably very hard to find a better strategy from here because it seems caught in a local optimum. Anyway, the point of using this vision-based approach to complete this visually simple track is that the same approach can in theory be applied to any track at all, right? So let us try something much more complex now. We will try exactly the same approach on this track from the official campaign. So visually speaking, it is much more complex. You can see that there are all these trees, all this stuff and different colors everywhere. Even the physics are so much more complex than the previous track. You have very long air times and big jumps everywhere, and you also have different kinds of terrains. You have road, but you also have dirt, and you even have water at some points. So, do you think our previous AI could complete this new track? Well, of course not. The previous AI was trained in a featureless environment, very simple, and it has no idea how to deal with all this new stuff that it has never seen before. But it is still kind of trying something here. Now the real question is what happens if we train the same vision-based approach from scratch on this new track? And I have done this for 30 hours of training, so now please let me show you the results. Anyway, what you just saw is not very fair because I have selected the best run out of 1000 of my final policy. Now here are the 1000 runs of the final policy that represent the actual performance of the policy. You'll see that it has a lot of variance because probably even after 30 hours it was not fully trained.